Hello everyone and welcome to Lecture Today. Today's lecture will be extending what we talked about in the last lecture, which was Green's theorem in the plane, which itself was a sort of generalization in some sense of the fundamental theorem of calculus to vector fields in 2D. Today we'll be extending that in two different ways. We'll see the extension known as the Kelvin-Stokes Theorem, and we will also see the extension known as the divergence theorem. And these really are two of the most fundamental theorems of calculus because they do exactly what I just talked about. They extend even further the idea of the fundamental theorem of calculus. So the idea here is we'll kind of jump right into the first theorem that we're going to talk about today, which is called the Kelvin-Stokes Theorem. And recall that Green's theorem in the plane under certain conditions on the vector field F in the domain R is giving us that the circulation of a vector field F around the boundary to R, what we'll call the boundary curve C, the piecewise smooth boundary, is exactly equal to the double integral of the curl of the vector field F over the region R. This is for a simple domain R. The boundary is a curve C, and the region R has no holes in it. And the vector field F is a 2D vector field. And a natural question is, can we directly extend this idea? And this is something that we can definitely do, and what we'll do is we'll draw a diagram, kind of a picture, to see how we're going to go about extending this idea. This is Stokes' original construction. So let's consider that we have some curve in three-dimensional space that's oriented in the counterclockwise direction, or oriented in some specific direction, and this is in three-dimensional space. And attached to that curve, we have some surface in three-dimensional space, S. And we know that on that surface we can define the unit normal vector field. Color that here in red. Where at any point the unit normal vector is perpendicular to the surface at that point. Furthermore, assume that the surface is immersed in some vector field F. This is in general now a general vector field. So F has component P of X, Y, and Z, Q of x, y, and z, and R of x, y, and z. And we know that we can take the curl of f as well. And just like before, I mentioned that the curl of f is going to be important to us because if you remember from the Green's theorem that I just wrote down, Green's theorem in 2D is saying that the circulation of a vector field f around a curve C is directly equal to the accumulation of the curl inside the region R. This is our form of Green's theorem when there's no holes in the domain. And it turns out that under suitable differentiability conditions, this exact same thing applies. So at each one of these points on our surface, we can also plot out the curl vector in general. It's going to be, in general, this will be pointing in some direction. So this is at some point. The normal vector here is n hat at each one of these points, which in general it will change as you move along the surface. And we also have the curl of f. The curl of f, say, maybe here, points in maybe this direction. And here it could say point in this direction. And here it could point in this direction, say. So the Kelvin-Stokes Theorem is the statement that the accumulation of the normal component of curl, or the component of rotation around, the accumulation of rotation around every single point on this surface is going to be exactly equal to the circulation of the vector field f around the boundary. We'll see that it's a direct extension of this idea of Green's theorem in the plane, but it actually extends to general surfaces in 3D. Nice way of thinking about this is if you consider, say, multiple different patches of this surface. Let's just consider two very small patches along the surface. We cut along one direction of the surface and then along a perpendicular direction of the surface. Alright, it'll look like this. So if you consider the rotation of the vector field on each one of these small patches in the direction consistent with the orientation of the surface, this will give you some idea of what this theorem is going to say for us, because if you consider a bunch of small, very small patches on the surface, the rotation along this patch right here, rotation along this patch right here, I'm going to blow this image up a little bit. You can kind of see what I've drawn here is just a diagram demonstrating four separate, very small patches on the surface. But it shouldn't be hard to see here that on each one of these small patches, if we consider the relative curl in each one of the patches, the curl here, say, the curl here, and the curl here, If these patches are small enough, we expect that the curl or the circulation component along this patch, this portion of this rectangle is going to be canceled out by the curl along this rectangle, and the curl or circulation component along this rectangle is going to be canceled out by the circulation component along this rectangle, and so on and so forth. So the idea here is that we can continue this process out in both directions, perpendicular directions as well, along the surface. And what we're seeing, if we kind of think of this in general as this like propagates all the way down to the boundary, is that we expect, hopefully, that there's some very nice relationship between the accumulation, or the surface integral of the curl on the surface S, and the circulation of the vector field tangent to the boundary C, or the action of the vector field tangent to the boundary C. Just like with Green's theorem in 2 dimensions. Only this is now for a 3-dimensional surface that satisfies certain conditions. So this is exactly what we're going to see when we do out the improved Stokes theorem, or the Kelvin-Stokes theorem. So we need a couple different basic baseline assumptions that we need to make in order for the proof to go smoothly and work out nicely, and they're reasonable assumptions. So the first assumption is we will let S be a bounded piecewise smooth oriented surface in 3-dimensional space in R3, and furthermore we will let C be the boundary of S, a boundary curve. Could also consist of curves, multiple curves, depending on how complicated the surface S is. And this, by the way, is sometimes noted with a partial derivative sign next to C, or sorry, not next to C, next to S. Just to denote the boundary curve that bounds the surface S. So C is the boundary curve of S. That consists of finitely many piecewise continuously differentiable, or piecewise C1 simple closed curves. That are oriented consistently with S. All this means is that the boundary has to match the orientation of the surface that we're talking about. So the boundary curve C here is this curve right here, this lower curve. In general, you have the boundary curve C and the surface S. And the idea is that we're talking about the outward normal to the surface relative to the boundary curve C. So we're going around in this counterclockwise direction. The outward normal to the surface is pointing up. So we always need to maintain this this orientation and be consistent. As we've seen before, it's important to understand and keep consistent with all of your orientations, especially when we're going through and doing the integral theorems. This is really important. And our last assumption of the theorem is that we have to let f be a continuously differentiable or C1 vector field whose domain includes the surface S. So if all of these assumptions are satisfied, then the Kelvin-Stokes Theorem says that the total accumulation or the net accumulation of the curl of the vector field F normal to the surface S, for the total amount that F is rotating on the surface S, the net accumulation of that rotation is going to be exactly equal to the accumulation, or the total net accumulation of the vector field F acting tangent to the curve C, or the boundary of S. The curve C, which we defined before as the total circulation. So in equations, this ends up becoming that the surface integral over the open surface S of the curl of F dotted with the normal vector. Remember, that's the projection of the curl in the direction normal to the surface, or the amount of rotation around the vector direction of n hat, which is normal to the surface, ds. This is the total accumulation of the curl of F normal to the surface S. This is exactly equal to the integral over the boundary, the circulation integral over the boundary of the vector field F, which is the line integral of F dot dr. This is an amazing theorem, and I can't quite, overemphasize how incredible this theorem actually is, because it takes, and very, very nice idea from regular calculus or single variable calculus, and it extends it to multivariable calculus now. It's like saying, in some sense, the certain derivative of a vector field on some region is directly equal to the action of, or I should say it's the total integral of some sort of derivative of the vector field on some region S is directly equal to the value of f on the boundary in a specified direction. So this really is a nice generalization of a very, very fundamental idea in regular calculus to multivariable calculus now, and this is to the general case in 3 dimensions. So this also has an extremely large number of applications in physics. This is one of the central components that you need to actually derive Maxwell's equations of electrodynamics. You can use this to solve for, say, the flux of an electric field or magnetic field through a given object. We'll see an example in fluid dynamics a little bit later on, where this becomes very important for, say, calculating the lift on an airplane wing. The applications of this are endless, so I really can't overstate how important this theorem is. But let's go through and see if we can go through and actually prove this for the general case, and we're going to see that the proof is a little bit long, but it's worthwhile to go through and see. And really, what this proof breaks down to when we go through and show it is use of Green's theorem in the plane in a very special way. So we'll go through and prove this for a relatively simple surface. We'll assume that we have a parameterized surface. Surface S. And specifically, we'll assume that S is parameterized by some function R of uv for u and v in some domain C, some region D in UV space. And we've seen that many surfaces, all the surfaces that we'll be interested in have some sort of nice parametric equations that we can write the surface as. So this is the first thing. We assume that we have a surface that we parameterize as S, and the boundary curve C then can be parameterized by, and we'll connect this with the surface parameterization by saying the boundary can be parameterized by R of u of t, comma v of t, for t in some set I, where I is a subset of the real numbers, D is a subset of two-dimensional space, and the idea here now is that we have everything that we need to go through and go through and show this theorem using this parameterization. So it's important to point out that this is you know, we've seen many examples of surfaces that are more complicated than this. Specifically, you know, any piecewise surface. If you have, like, say, um, you know, like in the homework, you have to deal with a surface that looks like this, where you have a bottom and then the sides but no top, so sort of like a can shape. Or you could consider, like, surface that looks like this, maybe. You have a piece of the surface right here, and then a piece of the surface right here. Right. The idea, though, is that what we're going to see is that once we prove the Stokes theorem for a relatively simple surface that's going to be parameterized like this, the extension to piecewise surfaces is actually relatively straightforward and simple for any number of finitely many surfaces, or finitely many pieces on our surface. And what we'll do to start this proof is we start with the line integral portion of the proof, and we'll eventually move this into showing that it's the same thing as the surface integral that we got before. We start with f, the circulation of f dot dr around the boundary C. We know that when we go to evaluate this, this will be the same thing as the integral over the set I of f of u of t v of t dotted with dr dt dt. This is how we go through and evaluate our line integral in general over along a parameterized curve. Now, what's special here, and what we're going to have to point out, is that the position vector r, because of how we parameterize our curve relative to the surface parameterization, r depends on u and v, which also depend on t. So along our curve, r of t, or r of u depends on t and v depends on t. So we've connected the fact that we have a surface r of uv, and the boundary curve can be parameterized by choosing the correct u of t and v of t. But this means we have to use the general chain rule now when plugging in our derivative for our tangent vector dr dt. And the chain rule is saying that dr dt, remember, will be dr du times du dt plus dr dv times dv dt. This is the multivariable chain rule applied to this chain of dependence from multivariable calc class. So plugging in, then, this becomes the integral along I of the vector field f at u of t v of t dot product with dr dt, which is the same thing as dr du partial r partial u times u prime, or may use u prime instead of du dt, plus dr dv v prime dt. And this now simplifies very nicely. This becomes the integral over the interval I of f dot product with dr du and u prime dt is the same thing as, I'll just put it here, u prime dt is this integral plus the integral over I of f dot product with partial r partial v prime dt. This u prime dt is the same thing as du. We can think of it as, if we do a coordinate transformation, and the same thing right here, v prime dt, we can think of it as just dv. So this expression is nothing more than f dot product dr du plus f dot product with dr dv. And this is a line integral. It's actually a closed line integral over a boundary in uv space. So it's the boundary of the region in uv space that we parameterize in. You remember that this parameterization of the surface, if this is not the x-axis, this is the u-axis and the v-axis. The surface is parameterized over some domain D in uv space, and this line integral is being taken over the boundary of this domain D in uv space. So let's make a simplification here to kind of help us out with notation and kind of see where we're trying to go. We'll call this phi1. We'll call this phi2. This is the same thing as saying take the closed line integral over the boundary of D of phi1 du plus phi2 dv. It's phi1 and phi2. They're both functions of u and v, but they depend on u and v through the parameterization and also through the vector field f. And I'll give you a second to think about exactly what it is that we're going to do here, but notice that this uv space, because it's a parameterization of a surface, is in general some two-dimensional space. We can directly apply our Green's theorem from last lecture to this expression right here. So by Green's theorem in the plane, this is going to be the same thing as the double integral over the region D of the partial derivative of phi2 with respect to u minus the partial derivative of phi1 with respect to v. This is the integral, double integral du dv. And this is going to be the key, because this thing is going to actually reduce to exactly what we want. And what I want to do before I go through and actually compute this is kind of note a couple things. Right, remember that phi1 we've defined as being f dot dr du, and just for simplification purposes, I'll summarize some basic simplifications here. Remember that dr du is the same thing as the, I'm going to use subscript notation for the derivative, so it's xu, yu, zu, where each one of these subscripts stands for the partial derivative of the variable with respect to the variable in the subscript. Dr dv is equal to xv, yv, zv, and f, remember, is the functions p, q, and r. So phi1, or I should say not phi1, but psi1, this is the Greek letter psi. Psi1 is equal to p times xu plus q times yu plus r times zu, and psi2 is equal to p times xv plus q times yv plus r times zv. And so now when we go through and take the partial derivative, because in this expression that we're getting, we need d phi 2 du and d psi 2 du and d psi 1 dv. We need to subtract the two from one another. So we get d psi 2 du first. This is going to be equal to psi 2 is this right here, and for each one of these terms we're going to have to do the product rule, so it'll be dp du xv plus p times x uv, which stands for the derivative, the second derivative, and I'm just going to do one of these here so we'll kind of show what this means. xuv stands for the second partial derivative of x, first with respect to v and then with respect to u. Likewise, if I were to say do xvu, this is going to stand for the second partial derivative of x, first with respect to u and then with respect to v. My notation right here. So the derivative of this term with respect to u is this, then plus the derivative with respect to u becomes dq du times yv, which this is just the product rule again applied to this term, plus q times yuv. Then lastly it'll be plus dr du times zv plus r times zuv. And we have this other term that we got to go through and calculate again, which is going to be a little bit long. d phi psi 1 dv is going to be the derivative of this with respect to v. So it's partial p partial v x v, or xu, plus p times the v derivative of this, which would be xvu. the v partial derivative of this, which will be dq dv times yu plus q times vu. Then lastly, the v partial derivative of this, which will be dr dv times zu plus r times zvu. And at first this looks extremely daunting and overwhelming, but you'll remember that, and you can think about what the assumptions that we made in this problem about the continuity and the smoothness of our boundaries. Well, xuv, or the mixed second partial derivative, is going to be equal to xvu, because of Clairaut's mixed derivative theorem, right? And so the idea then is that, well, when I subtract d phi 2 du from d psi 2 du, or when I take d psi 1 dv and I subtract that from d psi 2 du in this double integral, you get a cancellation here, and so these two terms right here cancel out. You get a cancellation here, so these two terms cancel out, and we get a cancellation here. When I subtract these two equations from one another. And what that leaves me is the following. It's still a relatively long integrand. But what I'm left with is, when we go through and evaluate this, and I actually plug into this integrand, so I take this right here, subtract all of this out, and I plug it in here to this integration. I get double integral of dp du times xv plus dq du times yv plus dr du times zv and then subtracted from that is dp dv xu plus dp dv dq dv yu plus dr dv zu. UdV. This is the double integral that I get. Now, this is long, and you might be wondering how we're going to actually get exactly what we want. But rest assured, we will be able to get it. We're going to have to use the chain rule again one more time, though, and it's going to become a little bit longer than this as well. But so just kind of remember here where we are. We've essentially been able to reduce the circulation integral by the clever use of Green's theorem down to this this double integral right here over the region D in our parameter space, parameterizing our curve. So this is what we've shown so far. So I'm going to make a little aside here to do one more chain rule calculation that we're going to plug into this, and it will definitely get a little bit longer as well. But trust me, it's going to be beautiful when everything cancels and simplifies for us. So this p here is a function, the first function of the vector field. It depends on position r, which depends on uv on our surface. Right, so this p depends on x, on y, and on z, each of which depends on u and v on the surface. So the idea here is that each one of these derivatives in this expression, for instance for dp du, this is really equal to, in terms of x and y, dp dx times xu plus dp dy times yu plus dp dz times zu. And same thing with dp dv. You're going to take the derivative of p with respect to v. The multivariable chain rule states you got to go through all possible paths of dependence for p depending on v. This is dp dx times xv plus dp dy times yv plus dp dz times zv. This is the multivariable chain rule for the partial derivatives of p with respect to u and v. You have to do the same thing for q and r as well. I'm not going to write those out, but I suggest you go through and just maybe refresh your mind on the multivariable chain rule from multivariable calculus. And the idea is that this is not going to be nice. When we plug in here, we're not going to get something super nice, because it's going to be a little bit longer than this. I shouldn't say a little bit, it'll be a lot longer than this. And so I'll take this in multiple different parts. So when we plug this in, we plug in here. This is going to be the double integral of dp du is partial p partial x times xu plus partial p partial y times yu plus partial p partial z times zu, all of this times xv. And before I even plug into the integral, let's just go through and see exactly what the integrand is. That way I don't waste any space here. So what we'll do is we'll call this entire thing, in parentheses here, the integrand, because that's what it is. And let's simplify the integrand right now. This is the first term in the integrand plus the second term in the integrand which is going to be dq dx times xu plus dp dx, or sorry, not q dx, but dp dx, but yes, it's the u derivative of q, which is a chain rule applied here, just like I did before. That's dq dy times yu plus dq dz times zu, all multiplied by yv and then lastly we have to add here the terms coming from this term right here, which is dr dx times xu plus dr dy times yu plus dr dz times zu all times zv. And this is the first terms in our integrand, so I'll surround all of this in a big parentheses. And now we have to subtract out all of this stuff, which will be dp dx times x v plus dp dy times yv plus dp dz times zv, all of this times xu plus dp dq dx times xu, or derivative of q with respect to v from the chain rule will be dq dx times xv plus dq dx, q dy, yv plus q dz times zv, all of this times yu and then lastly we have one more thing we got to add in here. That's this last and very final term, dr dv zu, which is going to be dr dx xu plus dr dy y or xv is the v derivative, or the v partial derivative, and yv plus dr dz times zv, and all of this is times zu. And you might say, whoa, this is not going to simplify at all. There's no actual hopes for simplification here. But you'd be wrong if you think that. If you kind of look at what's going on here, and you kind of cleverly think about what this long summation is, you'll find some really nice cancellations occur. Specifically here, you got dp dx. So right here, you have dp dx times xu times xv. Right, is that going to be canceled anywhere? Well, sure enough, this term right here is dp dx xv times xu. So this term right here is going to be canceled by this term right here. Here we have dq dy yu times yv, And here we have dq dy yv times yu. So this term right here cancels that term right there. And lastly, if you look at this dr dz zu times zv, this term is canceled by this term right here. It's subtracted out. And the remaining terms, remember this entire thing is our integrand. It's equal to our integrand. The remaining terms in the integrand can be grouped together into the following vector relationship. It's dr dy minus dq dz negative dr dx minus dp dz and dq dx minus dp dy. It's the dot product of this vector field with the vector yuzv minus zuyv negative xuzv minus zuxv xuzv minus yuxv. And what you'll hopefully recognize this as is the curl of our vector field F evaluated on our surface, R of uv, because all of these are evaluated R of uv, dot product with this vector right here, which is exactly partial r partial u on our surface, parameterized surface, cross partial r partial v on our parameterized surface. So this is exactly our integrand. Our integrand is the integral of the curl of f dot product with this vector right here, which you'll remember is the non-unit, but it's normal vector to the surface. And thus, we've shown that the circulation of f dot dr along the boundary is exactly equal to the surface integral, or we'll say the integral over d of the curl of f evaluated at the surface, r of uv, dot product with ru cross rv. Which, as we know, is exactly equal to the surface integral over S of the curl of F, vector field F, normal to the surface. This should be du dv here. This is an integral. So what du would be. Which concludes our proof. So this concludes the proof of the general Stokes theorem for this type of surface. So a nice, simple parameterized surface like this. Now, this can be directly extended to, and this is an important note, right? The above proof is only for a single parameterized surface. However, this is not too much of an issue, because as it turns out, right, for this happens in general, we have that circulation will in general cancel, and this is an important thing to always consider. You want to make sure you prove this, but for most cases that we'll find in applications, the circulation cancels along any piecewise smooth boundary. Due to the assumptions that we've made on the boundary of our shape. So it's relatively easy, right, to extend this directly. And I'm not going to go through the details of that, but I will show this for at least for an example. Consider you want to figure out the flux along one of the kind of piecewise smooth shapes that I talked about before. Let's use the generalized Stokes theorem to find the relationship between the circulation around some curve C, where C will be the circle, and say the circle looks like this, and cylindrical shape like a can. So S is the bottom boundary and the side boundary, but not the top. So we'll say, what's the relationship between the circulation around this curve right here and the flux, or the curl, the flux of the curl on S? And the idea here is the following, that this is a perfect example of a piecewise smooth surface, or a surface with a piecewise smooth makeup, because you have this side surface and you have the bottom surface. So the solution is to do the following. We will split this surface up into two parts. And we'll call the side S1. We'll call the bottom S2. We also have a bottom curve here, our contour around the bottom, which I'll call C1 as well. That'll be important. So because each one of these surfaces is smooth and can be parameterized, just like we talked about before, we can directly apply our general Stokes theorem to each of the small bottom surfaces. For instance, for the very bottom surface, double integral of the curl on S1 normal to, or sorry, not S1, S2. Or n hat here is the outward pointing normal to S2, which if we use I hat, j hat, k hat, it'll just be the k hat direction. This is pointing straight down. But this is going to be equal to directly from our general Stokes theorem, the closed integral around C1 of the vector field F dotted with dr. So the circulation around C1. And now this one is where it becomes a little bit more tricky. This surface integral around S1 of this side cylinder of the curl of F dotted with n hat, we have that it's going to be guaranteed to be equal to first the circulation around C, where C is closed, but we also have another bounding curve. So we have that this also has to be then added to this, the circulation around the bottom bounding curve. And you have to think about what the correct orientation for this bottom bounding curve could be. And the idea here is to kind of think of, well, if C is going around in this orientation, and we sort of look at what each individual boundary or each individual bounding curve looks like here. The bounding curve for C1, if C is going around clockwise, like counterclockwise, and we also said that C1 is going around counterclockwise, the curve C1 is also going to be going around like this. They're going to be going around in opposite directions, which is not consistent orientation, right? This is the bounding curve C, and this is the bounding curve C1. If we kind of stretch the cylinder out and just look at the orientations of these bounding curves, which means that for when we're applying Stokes theorem on S1, this means that the total circulation is going to be the circulation around the C with respect to this orientation. We have to flip the orientation of C1 to correctly apply Stokes theorem here. And the solution really comes about in a very nice way when we add these two things together to get the total flux over the surface S, which is the side of the can and the bottom of the can, both of these are coming from the theorem that we talked about before, or that theorem that we proved before, but this is telling us that then this is going to be the line integral over C of f dot dr plus the line integral over C1 of f dot dr, and then plus the line integral of along C1 with a reverse orientation, or minus line integral along C1 of f dot dr when I add all these things together. So we get a cancellation here. And what we're left with is exactly what I said before. Right, this is the general Stokes theorem. Even if we have a piecewise defined surface S, as long as all of the conditions are satisfied. So the flux sort of, if you calculate the flux in each of these small surfaces using Stokes theorem, you get a cancellation on this boundary, this piecewise smooth boundary. This is something that happens in general, and it's why we can definitively, very, very nicely use Stokes theorem in a variety of different, very clever ways. To really get a good idea of what this theorem is saying, Stokes theorem, we kind of want to be able to plot this out and see exactly what's going on. So what I'm going to show now is for that half a torus surface, what Stokes theorem is actually saying. This is true for any surface that we're going to evaluate Stokes theorem on. So let's consider that surface that's like the half of a torus from the previous problem. Where we argued for how to correctly apply Stokes theorem to the cylindrical can. And if we run this code that I've written, you see a picture of, say, a sample vector field. That's these black vectors, along with the unit normal vectors on the surface. So you can clearly see here the unit normal vectors at every single point on multiple different patches of the surface, along with some vector field f, which are the vectors that are pointing in different directions away from the normal vectors. Because this is a general vector field, we can interpret this as a curl vector field. So let's say this vector field f is the curl of some other vector field, and the idea is that we know that the amount of rotation at each individual point is going to be the normal to the curve is going to be the dot product of the normal vector at that point with the curl vector at that point. And that gives you the amount of infinitesimal rotation. So at all of these points, these base points, I've also plotted a colored point where the color corresponds to the value of this projection. The value of the dot product of the normal vector at that point with the curl vector at that point. So this corresponds to, say, this point right here is light blue, so this projection would be around a little bit over 0.5. And so on and so forth. You see that for each other individual vector that you can compute the projection. This one's red, so this is going to be in the negatives because the vector field, the curl vector field, and the normal vector at that point are not pointing along the same general direction. The idea is that we can do this at every single point. And what Stokes theorem is saying is that if we find the accumulation of all of these projections, so the accumulation of the curl normal to this entire surface, it's exactly proportional to the circulation around the boundaries. This surface has two separate bounding curves, so we have to add both of those circulations in the direction that's consistent with the normal. So if we look at that, the boundaries, right, the circulation is going to be around in this direction right here and in this direction right here. So this is why we had to switch signs before. But perhaps a better visualization here is going to come if we, instead of plotting this shows exactly what we're computing, but the vectors here are getting a little bit unmanageable to look at. So if we increase the number of patches on our surface, this picture is going to become more and more clouded. So let's just kind of draw, using the tangent vectors, a box of rotation in each one of these boxes, each one of these patches. And I'll hide the vectors, and the vector field and the normal vectors. When we do that, this is what picture results. So we can see here we have our surface, right? And in each one of these patches we have a rotation, and we're essentially measuring the amount of rotation the vector field is doing around each one of these points. So the color of each dot here corresponds to the total amount of rotation in this individual direction. And this is exactly what the curl is measuring at each individual point. The curl here is a little bit different than the curl here, a little bit more than the curl here. So these curls don't entirely cancel out at the boundary. However, what Stokes' theorem is saying is that in the limit, as these patches become smaller and smaller and smaller, all of these intersections, or all of these, the boundaries between patches, the curl is canceling out at them. And what that means is that the total amount of accumulation of curl normal to the boundary in this surface, so in this region, is going to be directly or directly equal to just the total amount of circulation on the boundary. And we can see this if we decrease the size of these patches. So as we decrease the size of the patches, it'll get smaller and smaller and smaller. However, we'll be able to see exactly what I'm talking about. So let's do this. In this picture we have 10 patches plotted. Let's increase it to just 15 and see exactly what I'm talking about. So if we increase the number of patches to 15, you can see clearly that these patches are getting smaller and smaller and smaller on the boundary, and the values of curl in corresponding regions that are close to one another are getting closer and closer and closer together. And as long as the continuity assumptions on our function are satisfied, this is going to continue to happen. So we need those smoothness assumptions on the vector field in order for this to happen. But as long as we have those assumptions, right, as we increase the number of boxes here, and so these boxes are going to get smaller and smaller and smaller as we increase the total number, and the value of curl in each neighboring cells is going to end up canceling out, so that this cancellation effect all throughout, and you have to go all the way to the boundary to compute the total circulation. Let's jump up to 25. So with 25, you see even more. This is going from 15 to 25. You see even more of what I'm talking about, where the relative amount of circulation in each one of these small boxes, or the curl in each one of these small boxes, is essentially canceling out. So the between these two boxes, the curl here is essentially the curl here. The circulation along these two edges cancels out, because each of these boxes we have to think of as rotating counterclockwise, and vice versa, all throughout this boundary right here, or all throughout this surface S. And it is getting a little bit, the picture even now is getting a little bit crowded, but you can see if you rotate it to a correct vantage point where you can see kind of the boundary, or even if you kind of rotate this around, see different parts of the boundary, you're seeing that very clearly. At each one of these boxes, the circulation is canceling out, because essentially it's becoming equal. And in the limit, as long as our differentiability requirements are satisfied, this is going to be the case. There's just one more plot here to show you that right? That surface integral of the curl in the limit, these boxes are getting really, really small. But as long as they, right, the requirements of the theorem are satisfied, because of the fact that these boxes are getting smaller and smaller and smaller, you get a cancellation effect in between neighboring cells, because the circulation here going down is canceling the circulation going up on this boundary right here. So that gives you a propagation all the way to each one of these boundaries here.